So today we'll talk about our work. Shesha is a multi-head microarchitectural leakage discovery in new generation Intel processors. So before we go into our work, I want to have a small background about transient execution. So we know that modern processors are all pipelines, so multiple instructions can execute at the same time, albeit at different stages of execution. So let us suppose that there are some instruction executing, and we have this instruction I and instruction I plus 1, and there is some data dependency between instruction I and I plus 1, and for some reason, if the instruction I actually has to roll back, and due to this data dependency, it needs to also reach to purge the instruction I plus 1. So basically, the execution that instruction I plus 1 has done is called transient execution, and although it does not has no effect on the memory or the registers, it actually keeps some footprints in the microarchitecture state. So previous works in literature have shown that these microarchitectural traces can be exploited across various components of the processor. But the one question could be, why such so many attack avenues or transient leakage avenues exist in the processor? The point is, finding these vulnerabilities in processor is a complex and time-consuming process. And if you look at most of these works, they need actual sophisticated mechanism and specific expertise. So our contribution in this work is to come up with a solution, to propose a solution which can automate this process of finding new vulnerabilities. So in this work, we specifically try to focus on something called batch speculation as termed by Intel, which mainly consists of microcode assists and machine clears. So these are the events that actually is taken up by the processor when it goes into some exceptional situations, and to recover from the situation, it uses these events. So in this work, we try to find out, or rather have an automated approach to find out a sequence of instructions that can trigger these kind of batch speculation events, and whether those events can eventually have some actual leakages. So for the automation part, we specifically try to look into something called particle swarm optimization. It's a pretty well-known variant of evolutionary algorithm used for search algorithm for searching for optimal solutions in the solution space. The unique advantage it has is that you need only the objective function, which is in this case is the hardware performance counter that tracks of different types of batch speculation events in the processor. And the two features what led us to choose this particle swarm optimization method among all other evolutionary algorithm or genetic algorithm as such is that it has these two features called exploration and exploitation. But exploration is basically a random search by each individual particles. However, this exploitation is basically a swarm nature where they kind of all the particles communicate among each other so that the entire swarm can behave as a single particle, such that each other's knowledge can be shared to have a better convergence toward the towards the optimal function. So now we use this particle swarm optimization based approach to create our tool Shesha. It's basically composed of 3 phases, where in the first phase, which we call the initialization phase, we create a set of ASM files of randomly generated n instructions, and we transform them into something called position vectors. So these position vectors are basically encoding of instructions and the operands, such that we can mathematically represent these instruction sequences to be used by the particle swarm optimization algorithm. In the next phase, which we call as the cognitive phase, we also again introduce another feature called velocity vector, which basically enables the sharing of information across multiple particles, and that leads us to create something we call as subswarms, where each subswarm focuses on a specific batch speculation event. So we can think of it like this, that multiple subswarms can search the entire search space, where each subswarm focuses on a specific batch speculation event, and they share the information among each other. And finally, we come to the mixed phase, where it is basically an optimization phase, where we remove the non-participating instructions from the ASMs such that at the end of it, you get an ASM which is very optimized, and it consists of sequence of instruction that can actually lead to different bad speculation events. So using this, we tried this process on multiple systems, more specifically Intel 12th generation and 11th generation client systems and Xeon 3rd and 4th generation systems. We found out 4 novel leakage, transient leakage variants, where the different instruction sequences, when mixed together, they show different types of transient events, and all of them actually show transient leakages, and while some of them also show LVI type of injection as well. However, to focus more on the practicality of these findings, we will delve a little bit deeper into something called fuse, multiply, add instructions.
Thanks. So in this work, we mainly focus on, from the exploitability perspective, mainly focus on the FMA instructions. So the FMA family of instructions, they fuse 2 operations in one go or in one instruction. So you could do multiplication, additions, subtractions, interleavings, and even do sign reversed multiplications. So if we talk a little bit about how the FMA execution architecture looks like. So here are a couple of Intel patents, and they look like any generic execution unit in modern day Intel architectures. So in the front end, you have units related to instructions and their associated micro operations, as well as a branch prediction unit. In the back end, you have units related to renaming, allocation, retirement, and the physical register files as well. But we are mainly focused on this particular aspect. So between the execution unit that takes care of the actual execution of FMA instructions and the memory unit, which is related to the cache hierarchy, we have something called memory access units, which we can think of as buffers. So it's quite well known by now that Intel and even other vendors as well, they have buffering optimizations, or like buffers that sit between the execution unit and the memory hierarchy in order to avoid the latency of memory accesses. And we'll also like to point out here that all FMA instructions, they have counterparts in which one operand can be a memory operand itself. So they try to avoid having another instruction to fetch some operand from memory and then operate upon it in the FMA execution unit. So it's quite obvious here that if there is speculation in the execution unit presented here, then there might be speculative forwarding from these memory access units. So we basically devised 2 sets of experiments. In the first experiment, we would try to look for speculative forwarding from these memory access unit to the execution unit. And the second experiment was to actually look for speculation between this particular unit, the FMA unit, and the vector unit, which is related to AVX, SSE, and the other instructions. And the reason for doing so was that even though here you see a physical register file for the FMA execution unit, but we know that the FMA execution unit and the vector execution unit share the same logical register file. So we were curious to see if speculation in one of them could lead to data leakages between the 2 execution units. Now, in the first experiment, we did not find any speculative forwarding. So in some sense, from this memory access unit to the execution unit, we did not find any speculative forwarding. We can attribute this to the fact that the transient window we create is not sufficient to hold all the operations within it. For example, the execution of the FMA instruction, fetching of the data from the memory unit to the execution unit. So all these operations may not fit well within one transient window. But the second experiment did work out. So on a co-located hyperthread, if there's a victim thread which is executing FMA instructions in a tight loop, and should we program the third operand here to a predetermined value, and if we force the co-located hyperthread into transient execution by using some like we used gather instructions here that comes from downfall, and one of the very nice ways to force the AVX execution unit into speculation. So if we do that, it turns out that data from the FMA execution unit can actually be transiently forwarded to the vector execution units. And this also leads us to hypothesize that the two units actually share the same buffers, even though they are two separate units in hardware. And this is a result of the same. So we use a generic flush reload covert channel to encode the transiently forwarded data into cache and then read it out from there. And if we talk a little bit about the implications of this, so FMA instructions, and more importantly their integer counterparts, they are being used predominantly to speed up cryptographic applications which require a lot of multiplications and additions. Like Montgomery multiplication is one very important aspect of several algorithms which uses this. So modular exponentiation, some works very recently have used IFMA instructions to this effect. So for instance, you have two cases of, an initialization state, and within a tight loop there is another IFMA instruction that is working on AI here, which is actually the multiplicand input to the modular exponentiation. And just by the example that I showed in the previous slide, it turns out that if you co-locate two if on co-located hyperthreads, if you force one of them into speculation, then actually this multiplicand can be leaked to the attacker basically. And a similar leakage we could also find on CSIDH and Psych, which again use IFMA instructions to speed up their multiplications and additions. So to conclude, in this work we basically propose to use particle swarm optimizers in order to search for transient executions. We choose PSOs because they have very expressive capabilities when the search space is very large. So for instance, most of our campaigns involved ASMs with more than 40 to 50 instructions, and it could be even more. So the search space, whenever it is very large, PSOs are one of the best optimizers to converge very fast there. And then also, we also come up with reverse engineering of the speculative paths which we report on the paper, and finally the FMA exploit that we have. So here's the QR to the artifacts which were also reproduced by the artifact committee. So if you'd like to have a look, and that's it from us. So thanks for listening, and if you have questions.
Thank you.